This video will go over select problems from the Introduction to Inverses classwork homework practice problems from the Overview of Functions unit in Algebra 2. Let's begin with number 263. In order to map the inverse functions, we have to recall the definition of an inverse. Inverses have all of their independent variables and dependent variables switched, meaning the x and y values are completely flip-flopped. So all your y values become your x values. So everything from the second column has to go into the first column. Everything from this column will go into the first column in our inverse, as all of our y values become now our x values. Next, we take all of our answers from the first bubble and we put them into the second, because all of our x values become y values in our inverse. And the mapping is still the same. So since 1 went to 2 here in the original function, 2 will go to 1 in the inverse function. The same with 5 and 4, 8 and 6, 11 and 9. And now from here, we can tell, is this a function or is this not? Since each value in your first bubble goes to a unique value in the second, the inverse here is a function. And yes, you can abbreviate function as FCN. Okay. Be careful when you do the next problem. As you can see in the next problem, we have some overlapping values right here. So that might play a role when we go to find whether or not the inverse is a relation or a function. If my values flip-flop for the inverse and I rewrite them in the opposite bubble, so my y values become x values, my x values become y values. At this point, I have to pay attention to where the arrows used to go. So since -1 used to go to 8, 8 now goes to -1. Since 2 went to 4, 4 now goes to 2. So far, so good. But now take a look what happens with 7 and 8. 7 used to go to 8, which means 8 has to go to 7. And look what happened now when we took the inverse. 8 now is going to 2 y values. 11 is still going to 9, but the 8 now has 2 y values that it is going to, which makes this a relation. It is not a function. Okay, so once you take the inverse of t, despite t being a function, t's inverse is a relation and not a function. Okay, let's move on to taking a look at the couple of points. In number 265, in order to write the function in its original state, we have to, again, reverse the x and y values. So my x values become y values and my y values become x values. So the first point becomes 2, 1. The second point becomes 4, 3. And the third one becomes 6, 5. And that's your answer. Okay, let's move on. To determine whether a function is one-to-one, we have to recall our knowledge of parent functions. And that's going to help us with this section. For example, for number 267, this is a square root function. Despite its transformation of horizontal movement and the a value expanding or shrinking the graph, you're going to have the same shape. The square root function inevitably always looks like this. So despite its transformation, it is still a one-to-one function. So yes, 267 is one-to-one, and you can do 1-1 to describe it. Now, when we go to 69, when we go to 269, the difference is 269 is an absolute value function despite its transformation. I'm going to ignore the transformation. I'm going to draw the parent function here because I know the parent function, despite any movement left, right, shrinking, widening, it doesn't matter. It's still going to be the same shape. Since my x values, since each y value actually leads to two x values, this is not a one-to-one function. So no, that is not one-to-one. Okay. Determining one-to-one functions graphically becomes a lot easier. The minute that a function does not pass the horizontal line test and only hit the function in one place at any given time, it's not a one-to-one function. So 271, that's a no. That is not one-to-one because you can see my horizontal line hits the graph in several places. So y values and x values are not unique pairings. In 272, though, we can see that no matter where I draw a horizontal line, the graph only intersects it at one spot. So this is a one-to-one function. Yes, one-to-one. Okay, let's move on to the next problems. For 273, this is a multi-part, and it requires us to use knowledge from several lessons that we've learned so far. So the first part of 273 asks us to determine what the inverse is of the function. And recall from the lesson to determine whether what the inverse of a function is. Instead of using f of x, I'm going to switch over to y. By switching over to y, I'm allowed to switch x and y easily, and it becomes more simple of a process to use y instead of f of x. So to find the inverse, I'm going to switch x and y. And now I need to solve for y, meaning I have to isolate the y variable. So I'm going to do this by adding 2 to both sides. That's going to get it started. I'm going to end up with x plus 2 on the right and 3y. I'm sorry, x plus 2 on the left and 3y on the right. Now I divide both sides by 3 to undo the 3. And I can see that my new function, when y is isolated, is x plus 2 all over 3. To identify that this is the inverse function, not the original, we now have to use that y to the -1 power, y inverse. Preferably, when you do list your final answer, you should go back to the f of x notation. So f of x inverse is x plus 2 over 3. Again, this notation is the same as that, and this notation is the same as that, right? F of x is the same as y, and f of x inverse is the same as y inverse. Now we have to algebraically show that the composition of the inverse and the original function is equal to the composition of the function and the inverse. That's a lot more complicated sounding than what it really is. What you're looking to do here is plug in the original function into your inverse and then plug your inverse into your original function. So for example, if we were doing f of f inverse, I would take this f function, 3x minus 2, and I would use that as my shell. So it's going to be 3 times something, not x, because I'm not plugging x into it, minus 2. Now, what I need to plug in is not x. I need to plug in the inverse. The inverse is x plus 2 over 3. This is where it gets really easy. Because they're inverses of each other, everything cancels out. So, see 3 in the numerator, 3 in the denominator? These go away. So you end up getting x plus 2 minus 2. Now look what happens. 2 minus 2, they cancel out. You're left with x. If two functions are inverses, remember, you're supposed to be left with x. So this checks out. Now we have to do it the opposite way. So I'm going to take the f inverse and I'm going to plug f into it. If I take f inverse is that x plus 2 divided by 3. So I'm going to have something plus 2 divided by 3 here. That something is going to be the original function, 3x minus 2. Now, again, they're inverses, so you're going to quickly see negative 2 plus 2, they're going to go away, and you're going to be left with 3x divided by x, and then the 3's are going to go away, and your x is left. So do you see how, despite plugging them in opposite each other, they both end up simplifying down to x? That's what inverses do. When you compose an inverse and a function, you are to get x simplified. If you don't, the two are not inverses of each other. Okay, let's move on to part C. I'm going to clear the drawings right now so that you can see these a little bit more clearly. All right. We had f inverse here was x plus 2 divided by 3. So now it wants us to graph the two lines. I'm going to first graph the function 3x minus 2. So I know I need to start at negative 2 on the y-axis, and my slope is up 3 over 1. So there's the graph of f of x, and you need to label it as f of x. Now I'm going to move on to my other function. If I simplified this down, it would look like 1/3 x plus 2/3. So I know that my y-intercept is at 2/3. And then I go up 1 and over 3 to represent the slope. And there is my f inverse. Describe the domain and range of f inverse for part D. Well, f inverse is a line. It's a straight line. So what's the domain and range of any line? It's infinity, negative infinity to infinity. So you can put negative infinity to infinity for both of these. Another acceptable answer would have been for you to write all real numbers, the symbol. So the domain and the range is all reals for your domain and range. Okay. All right. Let's try one more of these just to make sure you guys understand. I'll show you one more clearly worked out, and that should help you all finish this up. So let's do the cube one, the cube root one. So to find given f of x, we need to find f inverse. So we're going to work once again. We're going to switch x and y. And we're going to solve for y in order to find the inverse. So the first thing I'm going to do is cube both sides. X cubed equals 1 minus y squared. Now I'm going to minus 1 from both sides. So x cubed minus 1 equals negative y squared. I'm going to divide both sides by negative because I want this y to be positive. So I'm going to get y squared equals negative x cubed plus 1. And now I have to get rid of the square root. So take the square root of both sides, which means y inverse. Before I write that, let's just finish writing it. Y is equal to the square root of negative x cubed plus 1. But that's not the original function. That's our inverse function. So make sure you label it as x to the negative 1. Or y to the, I'm sorry, I apologize. You need to label it as y to the negative 1. Y inverse. And to formally rewrite it, we do want to go back to using f of negative 1x, f inverse of x. F inverse of x is equal to the square root of negative x cubed plus 1. Now, the next step is to do that composition. Again, you have to do the different, you have to put the function into the inverse and you have to put the inverse into the function. So if I'm doing the function first with the inverse inside it, I'm going to rewrite that first original function, cube root of 1 minus, and instead of x squared, I'm going to want to plug into it square root of negative x cubed plus 1, which is our inverse function. Now you can see very quickly the square and the square root are going to cancel out. You're left with cube root of 1 minus negative x cubed plus 1. That negative is going to get distributed, which changes the x to a positive, x cubed positive, and it changes this 1 to a negative 1. The minute this becomes a negative 1, the 1's cancel out, and you're left with the cubed root of x cubed, which now cube root and cube cancel out, and you're left with x. If you do when you do the inverse and you plug in the original function into here, you will simplify down to x as well. Okay. Okay, let's rewrite the inverse. For graphing these two functions, you can use a graphing utility because these are a little bit more complicated with square roots and cube roots and x squareds and x cubes. So what we do is we will use a graphing utility to graph them. When we do this, we will see that your graphs are here like this. It's your original, and that's f of x. And then your other function is right there as your original. I'm sorry. This is your inverse, and that is your original. Now, next part asks us for the domain and range of f inverse. We can see that the domain of f inverse is all real numbers or negative infinity to infinity. But the range, even though it's going down to negative infinity, it stops at 2. So our range is going from negative infinity to 2 inclusively. That concludes the problems from this section.